Well, welcome back to the Hab where we do math to save our lives, I guess. Well, right now we're going to be looking at components of acceleration. Where is it? There it is. So let's get right to it. Components of acceleration are just referring to the idea that when you have an acceleration vector, and I guess I never drew this, so let me draw the exactly what's going on. Just a minute. So let me take a minute to draw exactly what's happening with these vector functions. So here's a vector function, and you have to imagine that this is floating around in space. Why does it look like that? Hmm, just a minute. Okay, I don't know why it suddenly got small on me, but now I've made it big. And hopefully it won't get, I don't know. Just weird things happen. So anyway, we've got our vector function. You have to imagine it's floating around up there in 3 dimensions, not just the 2 dimensions that I have there. So um, anyway, just want to make sure everything looks okay still. Uh, so let's just pick a point here. So the position, where that is, the location, that equals r of t. So whatever, maybe whatever point you're at in time. And then the velocity is the direction you're moving. So this is v of t. And I just probably should have done this a little different. Let's get rid of this location business. Okay, so here, this is, we'll call that the position. I needed to clear out that inner space there because the deal with the acceleration is that it will point towards the inside of your curve. So your acceleration vector always points towards the inside of the curve. So as you're turning, your velocity is changing in the direction of whichever direction you're steering. So that's why the acceleration is always towards the inside of the curve. And not only that, but if you're going faster, if you're accelerating, then your acceleration will point, trend towards the direction of the velocity. And if you're decelerating, like you're putting on the brakes, then it'll go back here somewhere. But the important thing that I wanted to show you with this diagram is that the acceleration has 2 components to it. Let me pick a different color here. One of those components is this component. There we go. That component is called the normal component of acceleration, this black thing that I've put in here, a sub n. And then another part of it is the tangential part, a sub t. So when we talk about components of acceleration, we're talking about those. And we don't think of them as vectors. We don't use them as vectors. We're going to use them as number scalars. And the reason is that you already know what direction you're moving, and you can figure out acceleration. Those are vectors. And so you're going to take the acceleration vector and take it apart into 2 pieces, 2 components. One of those components is the component that is either making you go faster or slower. The other component is the one that you're feeling when you steer and you are smashed up against the door of your car. Okay, so getting back to components of acceleration. Tangential component of acceleration, you're going to compute in one of the following ways. But I'll tell you right now, it's the last way that's going to be the easiest way. So it's called a sub t, and it equals the scalar component of the acceleration in the direction of the tangent vector. You can also get this by doing the dot product of the acceleration with the unit tangent vector, but those are all difficult. And so this last one is the one that's the easiest. It's just the derivative of the speed. So This is how fast you're accelerating or decelerating. It's the derivative of speed, right? Okay, the normal component of acceleration, on the other hand, is a little bit more complicated to compute. It's the scalar component of a of t in the direction of the unit normal vector, which we haven't even computed, which also equals a of t dotted with the unit normal vector. But here's the easy way to compute this, is that I take the acceleration vector and I find its magnitude, and then I treat this like a Pythagorean triple. Whoa, can I go back to the next slide, previous slide? I don't know if I can. If I go like that, there it is. So notice that you have a right triangle here where you have a sub n, a sub t as the two legs, and then the hypotenuse is the acceleration itself. So anyway, that's what you're exploiting right here. And that's the way I would suggest you do this. So out of all of these, this is the formula that I use the most for the tangential component of acceleration, and this is the formula I use the most for the normal component of acceleration. So let's go ahead and use those. So we have this very simple situation. This is just an object moving in a circle. And I want to find the velocity first. I want to find those tangential and normal components of acceleration, but to do that, we start off computing the velocity, which is the derivative of position, so that's easy. Just do your derivatives. And we're going to compute the acceleration as well. Once again, relatively simple. Now, to find the normal and tangential components of acceleration, we first come up with the speed, and then do the derivative of the speed. So the tangential component of acceleration is derivative of speed, which in this case is just 0, because notice that the speed is constant. The normal component of acceleration will be the square root of the magnitude of a squared, sorry, I had to think for a minute there, minus the a sub t squared, which is 0. So that's also pretty easy. That's just going to equal the magnitude of a of t, because you're doing the square root of something squared. So I just have to do the magnitude of this. So let's go ahead and do this. Up here above me, it's the square root of negative 1/4 cosine of 1/2 t squared, negative 1/4 sine of 1/2 t squared. Whoops. So bear with me for just a minute. This won't take too long. This is going to be cosine squared 1/2 t over 16 plus sine squared 1/2 t over 16. I hope you're getting excited. I am. Whenever I see cosine squared and sine squared together, I immediately think, this is going to be easy to simplify. And it is. Cosine squared plus sine squared is 1. And so this ends up just being 1/4. And that is the normal component. All right. Okay, very nice. I feel like I only have the amount of strength to do one more of these. That one's too simple. That one's interesting, but I think this one is challenging enough that we should do it. And we'll call it a day. Okay, so we want to find all of those things. My goodness. Okay, we'll do it. V of t. I'm going to do this in a rather compressed form. 2tj t squared k. Oh, at t equals 1. So what I'm going to do is I'm going to compute all of my stuff first, and then I'll plug t equals 1 in here. Okay, so a of t is just 2j minus 2tk. In order to get some of these other things, well, let's get the unit tangent vector first. Unit tangent vector is the velocity divided by the magnitude of the velocity. So even though it didn't tell me to compute the speed here, I'm going to do that. And I'll do it up here since I ran out of room down there. So that's going to be the square root of 2 squared plus 2t squared plus t squared squared. Well, negative t squared squared, but it's going to become positive. So that's going to be 4 plus 4t squared plus t to the 4th. Interesting. That's actually a perfect square. But let's just fix it, because that's t squared plus 2 quantity squared. So this particular problem was kind to us. So anyway, to get the unit tangent vector, what we'll do is we compute the velocity 2I plus 2tj minus t squared k divided by that speed, t squared plus 2. We can make this look a little bit nicer, but we're kind of stuck with this the way it is. I will do this though. T squared plus 2, 2t over t squared plus 2 times j, t squared over t squared plus 2 times k. So there it is. Okay, the unit normal vector is the derivative of the unit tangent vector over the magnitude of that. And to be honest, I don't want to do it. I know you're going to have to do it on your homework, but this is like 3 quotient rules. I just can't face it right now. I mean, look where I am. There it is. Look at this. What am I doing? Okay, I'll do it in class. Ask me, and I'll do it for you. I just can't face it now. So you would do this. Do that. Okay. Enough of that. I'm going to put this in a little bubble. Hope it goes away, floats away like a little cloud. I don't think it's going anywhere. Okay, well anyway, let's finish this up. We got to do a sub t and a sub n. A sub t is the derivative of the speed. And look at this. Here's the speed here. So I'm doing the derivative of, doing the derivative of an equal sign, which doesn't make any sense. So doing the derivative of t squared plus 2, which is just 2t. So nice, easy tangential component of acceleration. The normal component of acceleration is going to be the square root of the magnitude of a. So I'm going to have to do the magnitude of a is the square root of 4 plus 4t squared. If you'll forgive me for not writing down all the details, it's pretty straightforward. So I'm going to stick that down. I'm going to square that though. So that's just going to be 4 plus 4t squared. And then you add to that, or no, you subtract from that. Ooh, that's amazing. This problem is working out so nicely. Maybe I should do this. Anyway, that's the acceleration squared. Subtract from that the tangential component squared. Incredible. So the normal component of acceleration is just 2. And all we have to do now is just plug this in. So I guess I'll change colors to do that. Let's see. So we'll do v of 1 is 2I plus 2j minus k. A of 1 is 2j minus 2k. Unit tangent vector at 1 is 2 over 3i plus 2/3 j minus 1/3 k. So all I've done is I've plugged 1 into all of this stuff here. Finally, and I'm skipping unit normal vector, finally we have a sub t is just 2 and a sub n is 2. Whoops, that's it. Okay, I guess we're done. Yeah, let's keep, oh, I discarded. Okay, rewind the video and pause it. Yeah, see, it is time to finish up. All right, well, I know you've got questions about this stuff. Please do bring them to class. I'm happy to answer those.